Hi, I'm Sophie, and you're watching The Science of It. This week, we're going to be exploring the mind-bending world of general relativity.
Imagine you're in a lift in deep space. There's no gravitational effects, you're just floating there. You're moving inertially, so we can say you're at rest. It would be the same if another person flew past with a constant velocity. They're still moving inertially, so we can also say that they're at rest. Einstein wanted to generalize the assumption he made in special relativity so that he could include the effects of gravity. So we need a situation that makes you feel like you're floating but also includes gravitational effects. Now imagine you're in a lift free falling towards Earth. You'll feel the same as you would floating in space, as you're falling at the same rate as the lift or the box around you. In this frame of reference, if you let go of a ball, it will just float next to you, as you and the ball are both falling at the same rate of 9.81 meters per second squared. If you let go of the ball in deep space, it would also float next to you, as there are no gravitational effects. So, can we say that these two situations are the same? Are they equivalent? This is the main idea behind the equivalence principle. Inertial mass is mainly defined by Newton's second law, force equals mass times acceleration. When you apply a force to an object, it will accelerate proportionally, and that constant of proportion is the mass of that object. Gravitational mass is defined by the force of gravitation, which says that there's a gravitational force between any pair of objects. G is the universal gravitational constant, m1 and m2 are the masses of the two objects, and r is the distance between them. As it turns out, these two masses are equal to each other, as far as we can measure. The equivalence of these two masses is also why objects fall at the same rate on Earth. If you attached an engine to your lift in deep space and started accelerating, you'd be able to stand on the floor, as the floor would be moving upwards towards your feet. If you were accelerating at 9.81 meters per second squared, and you dropped the ball again, the ball would appear to fall exactly as it would on Earth. In a similar way, if you dropped two objects with different masses, they would fall at the same rate, as you would expect on Earth. Einstein realized that space and time were connected in a concept called spacetime.
But before I go any further, what is spacetime? We know that space and time are connected, because if you want to meet up with someone, you're going to arrange a certain place and time. Because otherwise, you might never see them. So it makes sense that space and time are connected.
Essentially, the fabric of spacetime is a model that combines the 3 dimensions of space with the 4th dimension of time, and explains the weird relativistic effects that occur when travelling near the speed of light, as well as the motion of massive objects in the universe. Einstein published his theory of general relativity in 1915, and in it he determined that massive objects cause a distortion in spacetime, which is felt as gravity. So massive objects like Earth or the Sun can noticeably curve or bend spacetime, and you can demonstrate this fairly easily at home. The Sun causes spacetime around it to curve, and in turn, the curve of spacetime causes the orbiting planets to move in the way they do. In this setup, the marbles are mostly spiraling towards the centre, and this is mainly due to the friction between the marbles and the sheet, causing them to lose kinetic energy. But in our solar system, the planets don't lose energy as dramatically as this. So, although it might seem like the Earth will one day spiral into the Sun, it won't happen for billions of years.
Well, it's all very good saying that the more massive an object, the more it will curve space-time around it. But where's the evidence? We need proof, people. Mercury's orbit is actually the very first proof we have for general relativity.
You probably know that planets orbit the Sun in an elliptical orbit and not a perfect circle. According to Newton's view of gravity, Mercury would do the same, and it should stay in this elliptical orbit. But in reality, Mercury's orbit gradually precesses. This drawing is exaggerated, but you can see how Mercury's orbit is being affected by the curve in spacetime caused by the Sun.
Einstein also said that the star's position would change during a solar eclipse.
In 1919, a solar eclipse occurred just as the Sun was passing a distant star cluster. Scientists knew where the stars would be normally positioned in the sky, but if Einstein was right, when the Sun passed in front, it would curve spacetime and shift the apparent position of the stars behind it. But usually the brightness of the Sun would make the stars extremely hard to see. When the Moon blocked out some of the Sun's light during the solar eclipse, however, the stars became visible.
And this theory was proved to be correct by a British scientist called Eddington in 1919.
So all objects actually bend spacetime, even this melon. But when there's a huge amount of matter, like a cluster of galaxies, a gravitational lens can occur, as the gravitational field curves and magnifies light from distant galaxies that are behind it but in the same line of sight, sort of like looking through a giant magnifying glass. Individual stars, like our Sun, can also act as gravitational lenses when they pass in front of more distant stars. For a few days, the light from the more distant star appears brighter because it's magnified by the gravity of the closer object. This effect is known as gravitational microlensing. When the lensing nears perfect symmetry, a circle of light is produced, called an Einstein ring. Einstein figured out that if a massive object lined up exactly in front of a bright background source, we could see a bright ring of deflected light actually bend around the object.
So now, hopefully, you know a bit more behind the science of it. Thanks for watching. If you have any suggestions for other videos, pop them in the comments and I'll see you next time. So this is Spacetime. It's very complicated, I know.